Hello everyone. Now, in this session, we will be discussing about your second unit, Booth's algorithm. In order to compute arithmetic operations by the processor, especially multiplication, we will be using one algorithm named as Booth's algorithm. The purpose of Booth algorithm is to perform multiplication with different numbers. One might be your multiplicand and the other might be the multiplier. Both it is used to support signed as well as unsigned. Signed means either the multiplicand or the multiplier, any one can be negative number or both can be the negative number. Unsigned means both are positive. Both my multiplicand as well as my multiplier are positive numbers. So how does this computation is going to be performed? With the help of 2's complement notation. And this algorithm was invented by Andrew Donald Booth in the year 1950. So let me see an example of the binary multiplication of two positive numbers plus 13 and plus 7. Plus 13 is the multiplicand and plus 7 is the multiplier. First, we are supposed to identify the multiplicand and the multiplier, and both the numbers are supposed to converted into the binary format in the form of zeros and ones. So my 13 is going to be represented as 1101 and 7 is going to be represented as 111. Now we have to look for the length of the numbers. So here it is 4-bit representation, here 3-bit representation. Second step, we are supposed to equalize both. The length of the bits should be matched. The length of the bits of the multiplicand is 4 and the length of the multiplier is 3. So I am just going to append my MSB with 0. This is the binary representation of 13 and 7. Next, we are supposed to look for the sign, whether the multiplicand and the multiplier has positive or negative or any one or negative or both are negative. If both are positive, multiplicand is denoted as 0 and multiplier sign is denoted as 0. Why we are putting the 0 at my MSB? This represents what sign it is, whether it is plus 13 or minus 13. If it is minus 13, my MSB should be append with 1 instead of 0. If it is minus 7, it should be append with 1. Since it is plus 7, the sign indicates 0. The second step, we are supposed to convert that into 2's complement. If both the numbers are positive, so we are not supposed to convert that into 2's complement. As such, what the binary representation was initially converted, 0, 1, 1, 0, 1 will be followed as such, and multiplier 0, 0, 111 will be followed as such. The 2's complement will play a significant role only if any one of the multiplicand or the multiplier is minus. If the signature is negative, then only we will be going for 2's complement representation. Once it is done, step 2, we are just going to recoding the multiplier. So the multiplier value which was obtained in the first step in the binary format 00111 is going to be recoded based on the recoding table, and this we call it as Booth's recoding table. If 00 bit I and then bit I minus 1, bit I is the first position and bit I minus 1 is the previous position. If 0 and this position also 0, I have to multiplicand with the 0. If my bit I is 0, bit I minus 1 is 1, so this is plus 1. Bit I is 1 and bit I minus 1 is 0, the multiplicand is minus 1. Bit I is 1 and bit I minus is 1, so the multiplicand is 0. So we have to start recoding based on the reference of this table. So we are supposed to write as such the multiplier value 0, 0, 111. Since it is insufficient, I am appending 0 at my LSB for comparison. So I is my number first one position. Okay, so this is my first position denoted as I minus 1 is the previous position, so that is appended with 0. Now compare 1 0, so 1 0 indicates minus 1, then 1 1, this indicates 0, 1 1 again 0, 0 1 indicates plus 1, 0 0 indicates 0. So this is the recorded value which was obtained for the multiplier plus 7 based on this recording table. Now the obtained recorded multiplier value has to be multiplied with the multiplicand which was converted into the binary format initially. Now we have to perform multiplication. Multiplicand from the initial value we obtained as 01101, recorded multiplier recently we obtained as 0 plus 1 0 0 minus 1. We have to perform multiplication with this multiplier individually. So here there are some rules based on the recorded multiplier value. If 0 is there, anything multiplied with 0, I will get my result as 0. Plus 1, anything multiplied with plus 1, as such the same value will be obtained. If I am just going to multiply with minus 1, here this is a special case, we have to convert that into 2's complement and that will be my result. So look at here. So minus 1, if it has been multiplied with 0 1 1 0 1, so first I have to do the 2's complementation of this multiplicand. So 1 0 0 1 0 is our first complement. 2's complement, I will add 1 with the LSB. So I will be getting as 1 0 0 1 1. Now we have to check the length of the bit. If my multiplicand is of 5-bit representation, so my partial product should also be of the 5-bit length. So 5-bit length has been obtained as such. Now what is at the end of my MSB, that has to be append with another 5 more bits. So totally my partial product will be of 10-bit representation for each multiplier value. So I have to append with the end of 1. Now 0 multiplied with anything, I will be getting as 0. What the MSB is obtained, I have to append with rest of the digits. Now again 0 multiplied with 0, so I have to append with the ending number MSB 0 with rest of the bits. Plus 1 multiplied with the multiplicand, so I will be getting 0 1 1 0 1. So my MSB ended with 0, I have to append with 2 zeros. The last partial product, 0 into anything, so I will be getting as 0, so I am just appending with the 0 as an extension. Now obtained partial product is going to be added in the LSB 1, 1 plus 0, 1, 0 plus 0 plus 0, 0, 1, 1, 0. This will be the answer 10, 0 will be in the result and 1 will be carryover. 1 plus 1 plus 1, 3 ones means 11. So I will be getting like this, 1 plus 1, 10, again 10, again 10, and the exempted one is the carry. So the obtained result for this product is 000101101, and this has to be mapped with the decimal number. Step 4, verification. Plus 13 is represented in 5-bit, plus 7 is represented in 5-bit after recoding, and the result is 000101111 based on the code of 8421. So I will be having like this, 8421 and appended with 16 32 64. So 64 plus 16 plus 8 plus 2 plus 1, I will be getting as 91 as my decimal number. So 13 into 7 is 91. Hence both the answers are same and it is verified. Thank you.